All right, the third speaker is Chen Zhan. This is a collaboration effort that he developed with people from different places, so it's not one organization behind. Chen, please.
Yeah, thanks. It's my pleasure to be here. My name is Cheng. This is a joint work with Changjun, Li Cheng, Yong. So the topic is about decoding reverse time migration. Actually, at the beginning, we were thinking about applying the reinforcement learning to help us build better velocity model. And usually we try to QC the velocity model using some kind of migration. So that's our motivation why we have this piece of work. We want to build some kind of NL model that can somehow represent or approximate the RTM result. That's the motivation. So here is the outline for this talk. First, I will lay out some foundation for the seismic business. And then we plan to cover some of the existing work. Actually, last year, the people been using deep learning inversion to solve this inversion problem. Like they take the short gather as input to produce the velocity model. And here, what we try to accomplish is to do one step further. Can we produce directly to the RTM image? And we will take a close look at what's the fundamental difference between these two and what we need to do differently to accomplish that. And in the end, I want to spend maybe like 1 minute to talk about DeVito, since we've been using this fantastic tool to generate all our training data set. And actually, there will be a workshop on Wednesday about DeVito, so definitely attend it if you are interested. So first, let's start with this question. Can we hear the shake of a drum? The answer is no. In 1992, 3 mathematicians construct this example such that 2 drums with different shades that sounds exactly the same. That's actually the nature of inversion problem. The solution is not unique, even for simple 2D case. And you can imagine how challenging it is to solve for a 3D case. For the marine seismic survey, we try to reconstruct the subsurface structure based on the recorded seismic data. So usually we will start with some kind of initial guess. And then based on the recorded data, we try to construct the most likely subsurface structure. So you can think about that. We have some initial guess, and then we try to use the recorded data to recover the perturbation between the initial guess and the so-called true subsurface structure. So this involves fundamentally solving some of the wave equation. If you know about the velocity model, basically you know about how fast the seismic wave travel, so you can construct the wave field. And now the industry been using Freeform inversion to handle the inversion part. Essentially, try to formulate the inversion problem into an optimization problem. So since we have the velocity, and then we can use that one to construct the wave field. And then we compare the recorded wave field and the generated wave field and use the difference to update our velocity model. So as you can imagine, this involves solving a very difficult wave equation and also to update the velocity model, and usually involve many iterations. So that's why it's computational expensive. So last year, there's a paper talk about next generation of seismic velocity model building using the deep learning. So one of the selling points here is that once a good generalized network is built, we should be able to reduce the computational time dramatically. So of course, building a good generalized model is not a simple case. So then we will see how we proceed from this point. And the network they are using is this UNet, which is pretty popular for image segmentation. Basically, it's called UNet because it has a U shape. It's like the U shape, this component is to pass the semantic information, which like you try to understand the content of this input. And then on the top, there's some skip connection. Basically, as you go through the convolutional layer, you get more understanding about what is in the content, but you're losing the location information. So that's why we are using the skip connection to add those information back. So this is a typical use case for this UNet. And here the input is taking the short gather as an input, and then the output will be the velocity. So we did try to do a trivial extension, just to replace the output by the RTM, and it's not very effective. So that we went back and take a look what's the fundamental difference between velocity and the RTM image. So what's the difference? So velocity basically tells us how fast the seismic wave travel. And then the image is associated with a more complicated object related to impedance. So there's another dimension called the density information involved. And from a data science point of view, we actually want to model something simpler. For example, we just care about the velocity because the geometry is already very complicated and the inversion is not a trivial problem. So we don't want to overcomplicate the problem by modeling the image. That's one reason. Another reason is that actually from velocity to image, there's some kind of assumption we need to make. For example, talk about the reverse time migration. So there's an image condition here. Like we have the recorded wave field. And then we call it reverse time because we want to generate a wave field from receiver to shot. And then the assumption here is that if there's an event or reflector, then these two wave fields should have a strong correlation. So that's the fundamental assumption here. But if we do want to extend the velocity to the image, what should we do differently? So I will explain this in more detail quickly. So back to our workflow, we actually generate many velocity. So we start with the background velocity, like we have 8 layers of sediment, flat sediment. And then the thickness of each sediment is a random number. And then we go to insert a piece of salt. So it's actually a union of a simple convex shape together. And then we insert it to get our final velocity. So to give you an idea about how we generate this velocity, we start with the background velocity. And then we'll start with some simple shape, like a convex curve, convex. And then gradually we add another piece of complexity. And this will be the final one. So also we made the number of steps to be random. It could be 3 or more than, or 4 or even longer. So based on that, we have the velocity. We can use that one, use DeVito to get the shot information. And then using the shot and the velocity, we can get the RTM image. So that will be our starting point to train the model. So this is the so-called true velocity model. Basically, we are using the one we generated, and then run the RTM to produce the image. And if we run the UNet we see before, and the left-hand side is the RTM, the training data, and this is the prediction. So you can see the subsoil is not very promising. So next, I will explain why this method is not that promising and what should we do differently to get a promising result. So the architecture we are using is actually a 3 UNet with 2 UNet on the top and then 1 UNet on the bottom, okay? And then in the next few minutes, hopefully I can convince you this is the right approach. So think about the conventional method, how we run the RTM algorithm. So we will have the velocity as one input, which roughly speaking, give us an initial guess about the subsurface structure. And then we will take another input as the shot gather, which is the recorded wave field. So these two together will be able to recover the best, the likely subsurface structure. And then from a data science point of view, or machine learning point of view, we try to build something end-to-end, which means that just give me the input as shot gather, and then the output is the image. So we try to build a model to learn the RTM algorithm, okay. But even though we try to build an end-to-end solution, doesn't mean that we don't care about the intermediate step. So we also want to make sure that the intermediate step, supposedly we have a velocity, we want to make sure that the velocity is right as well. And also in the cost function, we can somehow minimize the difference between image as well as the difference between velocity. So that's how we combine these 3 UNet together. So on the top part, this is the shot gather. And then the first step is to get the velocity. And then the second step is from velocity to the RTM. Okay. And then this is passing the information mainly for the velocity component. And the reason is that we want to constrain to make sure that the loss function take care of this part and this part. And as I mentioned earlier, velocity is only one component for the final image. There's impedance component as well. So then we pass another information from here directly to the image. So the first part is to constrain, And the second part is provide additional information. So this is somehow to combine the data science architecture together with the physics information. How do we pass the information from short to together? So this is so far the best result we have. So the left-hand side is the velocity model, and the bottom part is the true RTM. And the right-hand side is this is the intermediate step. We output the velocity as well, and this is our final RTM. So I will say this is like perfect. There's definitely still room to improve, but I would say that this is actually very, very promising, especially compared with you using one single unit. The result is much, much better. And another thing we are still working on is regarding the loss function. So how do you measure the distance between two images? So far we are doing only pixel-to-pixel distance, but as you can imagine, that's only part of the story, because like for a seismic image, you want to look at certain structure. So inspired by Feifei Li and her team about this paper, so we not only take the pixel-to-pixel as the loss function, we also use some kind of a convolutional network to extract certain feature from the image, which means that you get some low-level structure about the shape of different segment or different sort. So this way, it can help you to get a better loss function that can help you to recover better image. So this is still working in progress, but we feel like this is actually another dimension to help us improve the result. So actually, in the field of computational fluid dynamics, there's some similar work. Like here, this diagram is modeling how fast the oil flow for a certain well. So the blue color the curve represents the result from the reservoir simulation. And the orange one is represent the ML model produced, the curve result from the ML model. As you can see, the decline curve, they look pretty similar. And then there's a cumulative curve. So basically, it's actually, hopefully this can be another evidence to convince you that this is reasonable to use the ML to represent whether it's the reservoir simulation or it's the inversion. It's possible to achieve that. And so in the end, I do want to spend like 1 or 2 minutes talk about DeVito. So on the high level, DeVito is a symbolic finite difference computation. And it helps to address two important questions in the upstream oil and gas. One is the computational fluid dynamics, which is super important in the reservoir simulation. The other is the seismic modeling and inversion. That's what we just covered about. Actually, DeVito is built on top of the SymPy, symbolic Python, which is a Python library for symbolic mathematics, which is a project carried out by Google. So it not try to solve the equation numerically. Instead, it try to get some analytic or symbolic solution. For example, you get a differential equation, you will have to get the analytic solution. So that's the DeVito. And we can use DeVito to run the full modeling from velocity model to get the short gather and also to get the RTM image. So that's actually how we generate all the training data set. And in terms of the discussion, so for the business value, we do feel like this could be a second opinion for the fast track. So if you don't have time to run every single process, you can just use this model from short to the final product. It will give you some idea about what does the subsurface look like. And in terms of the MVP, the minimum viable product, hopefully this can reach certain level that can help people narrow down the sweet spot much quicker. And for the future work, definitely, like I mentioned earlier, different migration have different assumptions. So we can extend this to different migration algorithms, for example, Kirchhoff. And also, eventually, we're still thinking about how to apply the reinforcement learning to help us build better velocity model. So that's the future work. And thank you for your attention. Yeah.
Thank you, Cheng. You have 5 minutes for questions.
I get a microphone. Hi. One is I'm going to indulge in two short questions because one is very technical and short.
Sure.
When you add the convex hulls, how many points are you randomizing for the salt block generation? Because it matters
Yes.
the complexity.
Right. I think around, if I remember correctly, around around 7 to 9, that range.
Does that give you enough expressivity with respect to the realism of how those sediments?
Yeah,
actually
that's a
behave?
good question. So basically, we did try different random number for that one. We feel like that's actually getting us close to some of the SEC benchmark. Yeah,
Okay.
so that's why we picked that number.
Okay,
Yeah.
cool. Second question is more when you talk when you talk about the application of reinforcement learning, what's the sequential decision-making process that you're actually having in mind for this?
Yeah, exactly. I think that's a very good question. I think actually we don't have a clear picture about that one yet, because actually when you first try to do the reinforcement learning, you need to have a simulator that hopefully that's very quick to tell you, give you some kind of idea about that. So we are still working on this one here. So after this one finished, we will jump into about that sequential. But that's very challenging because they think about how do you change the pixel for that event, and then how do you penalize that? That's actually, I don't think it's a trivial problem for that one.
Think of it like as moving in layers of abstraction.
Right. Yeah.
Interesting.
Yeah. Thanks.
Thank you for the talk.
Thanks.
Thank you. I think very nice talk. I just had one question. So you said you tried the 3 units which outperformed than the single units. So I think you mentioned the velocity kind of served as a constraint for the imaging.
Yeah.
Is that just one reason, or there are other?
I think
reasons?
there's multiple reasons for that. It's like one definitely I think a main reason is from the velocity, because like think about that you want to somehow, if you want to sell this model to convince the geophysicists to use your model, you need to somehow output some velocity, and then so then they can QC. And then also there's other reason as well, some kind of idea mentioned here. Like think about the ski connection, the UNet. That one is good if the 2 input-output are in the same domain, right? But now it's an inversion problem. So it's from time domain, which is the recorded wave field, to the subsurface structure. So it's a depth domain. So in addition to the 3 UNet, we also add another layer of complexity, which is some convolutional on the ski connection. So we think we test that. It seems to bring additional information for the localization information. So there's some other thing we change. Yeah, but the 3 UNet is the main driver.
And when you train the 3 nets, are you train at the same time, or you first train like velocity?
It's trained at the same time.
Same time.
Same time. So the loss function actually have a 2 component. We just output the intermediate step, which is the velocity. And then loss function have a 2 component, which is the loss function for velocity combined the loss function for RTM image. So that's how we get this one.
Oh,
yeah.
Thank you.
Sure.